The rate is decreasing. Yeah. I'm sorry? Well, we have three graphs that we can make up. Concentration, natural log of concentration, and the inverse of concentration. And two of those will be nonlinear, one will be linear, depending on what order it is. If we just look at the rate itself is given by the concentration versus time plot. And there are three of them that we'll see. One, it's just a straight line. The other, it's a curve, and there are two types of curve. You know, first order curve and a second order curve. And so that's what I mean by linear versus nonlinear in the concentration. But all of them will be linear in their respective plot. Okay.
So they all have constant half-life?
No. No.
Just the first one?
Only first order. First order has a constant half-life. Zero order, the half-life decreases. And second order, the half-life increases. So, if you only have three choices of plots, you can see which one you have just by looking at the half-life if you have enough data. And so to do the half-life, you just cut this in half, so that's about here. You see how long it takes. And then you cut it in half again. So we start here now, we cut that in half and see how long it takes. And you compare the first half-life to the next half-life, and you see that the first half-life is a lot longer. And so the first half-life is this long, the next half-life is shorter. And if we were to actually calculate it, it's half as long as the first half-life. If you have a first order curve, then you can take a look at the half-life here. And so the first order, we cut it in half, see how long it takes, that's T1 half. And then we start here and then cut it in half. So we get out to here, and then compare. Well, in first order, the two half-lives will be the same, exact same length. And then in a second order, decays like this, so that the first half-life, let's say, takes this long, but the next half-life, which would be about here, would take a longer period of time. In fact, if you were to calculate it, it takes twice as long. So each subsequent half-life. So the next half-life after this will be way out here. Yeah, and the slope, right, the slope will be cut by a fourth. Whereas over here, the slope is only cut by halves. And so if the slope is cut by a fourth, that means this one slows down much faster, the second order, than the first order. And so the second order reaction will take much longer amount of time. All right, other questions? Increasing half-life. Actually, there are only three choices, so it's either the half-life stays the same, first order. Half-life decreases, zero order. Half-life increases, second order. So, yeah, zero order has decreasing. So if we look at this zero order plot here, the first one's here, the next one's here, and then the next one, we cut that in half again. You see each half-life has to get shorter and shorter in order to match this curve here. And so zero order has decreasing half-life. First order has a constant half-life. And so therefore, we can describe first order reactions either by using the half-life, which I didn't talk about, you know. The half-life for first order reactions given by this T1 half is equal to the rate constant over 0.693. So we could either use the half-life, which is a constant, or K. Over here, the half-life is not a constant, so typically the zero order will represent using the rate constant K. The bigger the K, the faster the reaction. And the same thing over here for second order, we use K. But for first order, we like to use the half-life because it kind of gives us an idea how long it takes for you consume. The half-life for reactions varies from very short to extremely long, depending on what reaction you're looking at. When we get into radioactive decay in chapter 25, then we'll look more at half-lives. This is what they call the chemical half-life. There's also like a biological half-life. Have you ever heard of that? Biological half-life is how long the drug takes to I don't know, excrete or.
What's the constant rate for second order half-life?
1/. It's not a constant rate. The rate is always changing for second order. But if you plot second order using 1/, the concentration versus T, then it's linear, the straight line. But that's not the rate. It's just the integrated rate law relationship. So. Well, K is constant for all these. K is a constant for all three. All right, other questions? Yes. No. Well, what we can do with kinetics is we can make predictions. We can predict how long it's going to take or how much we'll lose or how fast the rate is at any point. Those come from just analyzing these curves and coming up with a mathematical equation describing these curves. But this chapter we're going to go into it a little bit deeper because we're going to look at some of the theory. This is unlike, for example, the equilibria chapter. The equilibria chapter, we just came up with an equilibrium expression. K is equal to some mathematical equation. But here we have the rate. The rate is equal to some expression, some mathematical equation. The rate for some generic reaction is going to be rate is equal to Ka to the m, b to the n. So the question comes up, where does m and n come from? What do m and n depend on? M and n are what we call the order with respect to A, that would be M, and the order with respect to the concentration B would be N, etc. We could have some more. The overall order is what we observe as far as the reaction goes. The overall order is going to be M plus N plus, however many we have in there. And then K is the rate constant. And so we're going to try to get a deeper picture of what M, N, and K are and what they depend on. And so it turns out the order, these come from the mechanism of the reaction. More specifically, M is the molecularity of the what we call the rate determining step, which is the slowest step. And so what a mechanism is like a detailed description of how the reaction takes place. And so if we consider some reaction like methane, we burn methane in O2, So 1 methane, 2 O2s. So we yield a CO2 and 2 waters. And so it looks like this reaction, all we're doing is we're colliding or getting a methane to react with 2 oxygens. So we could do that. It looks like a simple enough reaction, and this reaction has been known for quite some time. Oh well. I guess I'm not going to do it. But if we were to burn methane, right, and we want a detailed description of what's happening in the combustion, then we got to describe everything in there. And so have you ever burned methane and looked at the flame? What color is the flame? The color of the flame is blue. And so where does the blue come from? You know, that would be, well, that's what scientists do. They try to describe things in detail. So let's try to describe where that blue color comes from in detail. And so one thing the blue color might come from is water, right? Water is blue. Is that correct? Water is blue. Is water blue? What do they call the blue planet? Because water is blue. Well, okay, if it's not water, then what's blue? Is it the methane that's blue? Methane's blue? Well, methane doesn't look blue. Well, okay, is it the reaction? Because these are all colorless, right, including water. And so what's giving it the blue color? Well, what about the reaction? Well, usually things that come out colored like that have excited electrons, right? And so what do? Did we excite the electrons in water, and that's what causes it to be blue? Or if we excite, well, what is combustion? Is this reaction? This is a redox reaction. This is a combustion reaction. So here we have our combustion reaction, but incomplete combustion. Oh, is it the oxygen? Is it the O2? Well, is it incomplete combustion? Well, no, I could do a complete combustion and it still comes out blue. And so, is it the oxygen? Well, this room is filled with oxygen, 20% oxygen. Do you see blue? Now, if you were to excite the oxygen in this room, maybe, you know. Well, is there liquid oxygen in? I don't see any liquid oxygen is the problem. It's all gas. And so, you know what? What we see here is the net reaction. We don't see the mechanism. The mechanism details, you know, how the bonds are broken and how the bonds are formed. You know, and this is a gas, so what collisions do we have between molecules that cause these reactions to occur? And so, what the mechanism would show is, okay, you know, what is colliding with what and what's happening. And all that is missing here. And in fact, it wasn't until maybe 30 years ago that somebody finally figured it out. You know, this reaction has been known for a long time, but people just didn't know everything that happened in going from reactant to product. They could see the initial reactants, no problem. They could see the final product. What they wanted to know was what's all this other stuff. You know, the blue color is actually from atomic oxygen, you know, being excited. So do you see any atomic oxygen in this? No, we don't. But that's part of the steps. And so it turns out that this reaction is not so simple. When we look at this net reaction is made up of a whole bunch of smaller steps. Those smaller steps are called fundamental processes or simple collisions, you know, and here we'll have this collide with this, and this bond's broken, this bond's formed, and these are a product. And so the net reaction is made up of a whole bunch of simpler steps, and each of these simpler steps are, you know, there could be branches here, give us something else. And I thought I read, I read about like not so long ago that they finally figured out all the potential little steps in the combustion of methane, and that number came out to 1,000, over 1,000 different little steps occurring here. You don't have to go through all of those. I mean, they'll branch out and then eventually they'll reconverge, But what we have is we have a whole bunch of steps in the mechanism that we don't see because all we're looking at is the before and the after, but not what happens in between. Well, for the kinetics, we're mostly interested in what happens in between because the order M and N depend on which one of these is the slowest step. So let's say all these steps will converge and eventually they have to pass through this step here. If this step is the RDS, which we call the rate determining step, RDS, or the slowest step, then this presents what we call a bottleneck in the overall reaction. And so let's say all these other steps are quite fast, and then all of a sudden we get hit with this, and then they go fast again. And they could branch out or whatever. And we know that there are hundreds and hundreds of different steps in here. Then the speed of this reaction is going to be limited by the slowest step. The slowest step is always going to dictate how fast this reaction can go. So if you're in a long line of cars like this, the slowest car is going to dictate, how fast all the other cars go. And so this slow step here is where we get M and N from. M and N tell us, the molecularity, which I'll talk about what that means later, of this slow step. And so this is the origin of N, etc. So we can't use the coefficients here, A, B. When I look at the coefficients, A is 1, B is 2. Those don't go here because we don't know, in this slow step, is it 1 methane and 2 oxygens that are participating, or is it something else that's participating that we don't see? And so it's hidden. Now, the rate constant K here is going to depend on a couple of things. But we can figure out what K is. Actually, K we can get theoretically as well. K is going to equal A, e to the minus EA over RT. A is called the frequency factor. EA is what we call the activation energy. T is just the temperature, Kelvin temperature. R is the gas constant, the thermodynamic gas constant, the 8.314.5. And so we can see how K is going to be impacted by temperature. If the temperature goes up, then this term becomes bigger, and K becomes bigger. And so the rate constant gets bigger as the temperature increases. But there are other things that impact this too, the frequency factor and the activation energy. And so let's take a look at those. Here. When we think about the kinetics, we look at collisions, collision theory. In order to have reaction, we have to have a successful collision. So what is a successful collision? A successful collision is going to have enough energy. Because typically in a reaction we got to break bonds and we got to form new bonds. And so when we look at the energy, we can go back in chapter 6 and look at like a speed distribution and then translate that into a kinetic energy distribution. So if we look at E sub k, which is the kinetic energy, and the population, we'll see at 25 degrees C, not all molecules have the same kinetic energy. We're going to see a distribution of kinetic energies. And that distribution is going to have some root mean square, you know, or actually some average kinetic energy, which is going to be over here, which is going to be related to the temperature. And so this is our kinetic energy distribution at 25 degrees C. Let's say the bonds are pretty strong. Well, they're going to require some minimum cutoff energy here to break. That minimum cutoff energy is going to be related to the, you know, activation energy here. And so one way of thinking about the activation energy is the amount of energy required to break the bonds in the reactants. And so if we can't break any bonds, then we aren't going to form any new products. So most of the molecules here are unable to break any bonds because they don't have enough energy. But any molecules with an energy greater than E sub A will have enough energy to break the bonds. The impact of temperature on this distribution is to shift it. You know, at lower temperatures, the distribution shifts to lower kinetic energies. At higher temperatures, the distribution shifts to higher kinetic energies. So if we were to increase the temperature, we'll see that the result of that will be a higher population of high energy molecules. And so this would be high temperature. That would be low temperature. And so what this equation does is it fits that distribution, because that distribution is going to depend on the temperature, you know, how that population is distributed, and the cutoff. The cutoff is the activation energy. We need a certain minimum there. All right. So we need enough energy in the collision to break some bonds, but we also need.
Yeah, so I was wondering if any deviations would affect the rate of the
Any what?
deviations
Deviations from ideal behavior will affect the rate. It could. I mean, it could prevent things from colliding if they're held, you know, by intermolecular forces of attraction. But that would probably be a pretty minor effect. So it shouldn't be. I mean, the only deviations would be for gases would be the intermolecular forces. And that would impact the pressure, which could impact the next thing. And the next thing is we need to have the proper orientation. And so if things are hindered, it might, but don't really worry about deviations too much. For orientation, let's say we need to have two ABs collide, and they have to be oriented like this. Because what we're going to do is we're going to have these collide to make A2 and B2. And so what has to happen is this has to go like this, so that when these come together, the two A's, actually let's go like this. The two A's will start to form a bond while the AB's bonds are breaking. And so here we have these two bonds being formed while these two bonds are being broken. And the amount of energy to make something like this here, we call this the activation energy, E sub A. It's going to be a hump there to break. And so how much? It's not just bond energy, because if it were just bond energy, then we're looking at bond breakage. But we also have bond formation, so that's going to mean it's probably going to be a little less than the bond energies that's required. But in order to have the right orientation, so for example, if we had it collide like this, this might not result in a successful collision here, because here the orientation's off a little bit, and so let's say they're perpendicular to one another, and then we aren't going to get the bond formation, bond breakage that we need in order to see this. And so A, the frequency factor, is going to be impacted. How probable is it to have a collision with the right orientation? And how frequently are these molecules colliding? And so the frequency factor should factor that in. And so the more frequent and the more probable it is, the bigger the A is and the faster the rate is, because the bigger the K, the rate constant, we'll have. And so, so studying kinetics has practical purposes, like you can predict how long it will take for example, milk to spoil. That's one of the homework problems. But it also has some interest beyond that, and that is, the whole idea of getting insight into the mechanism of the reaction, how the reaction actually takes place. That's another major reason to study kinetics. Insight into the mechanism. Because people want to know, how or what is involved in that particular reaction. And so we're going to look at some simple mechanisms to start off with. In fact, actually, that's all we're going to look at, are a couple of simple mechanisms. The first reaction, actually, let's take a look. Be this, 2NO plus an O2 yields 2NO2. These are all gases. So we start thinking, well, how are the NO and the O2s going to react to form NO2? And then we come up with some possible collisions. The possible collisions that we're going to have, one is called a termolecular collision. A termolecular would just be three molecules colliding. So in a termolecular collision, let's say I have an NO that collides with an NO that collides with an O2. We need these to collide. And this would be a fundamental step, so there's nothing hidden. It's going to be what we call single step. When we have a single step, it's a fundamental. or elementary process. And what that means is this. When there's nothing hidden here, then this. For fundamental processes, the rate law is very simple. If we have a fundamental process is AA plus BB plus CC, something like that, and this goes to product, then the rate is just given by Ka raised to little a. We don't have to call it M because we see what the collisions are here. And that is, we need a certain number of molecules of A, and so that's what we call the molecularity, how many molecules of A participate in the collision. Let's say it's one molecule of A that participates in the collision, like over there, NO. And then B, well, it turns out A and B are the same combined, another molecule of NO. And so we need a left NO molecule to collide with a right NO molecule. Now think about this. If I double the number of left NO molecules, if I double the concentration, what should happen to the number of collisions? So if I double the population of NO, will the number of collisions stay the same as before? No, they're going to increase. Okay, so if I double the population of NO, will the number of collisions double, or will the number of collisions quadruple? What do you think? So if I double the number of NOs, let's say, just think about the collisions with the wall. If you double the number of NOs, are you going to double the number of collisions with the wall, or? Yeah, it should double. You know, you have twice as many molecules, so you expect the number of collisions to double. And so this is going to be first order in NO. Let's see B, the second NO here. If I double the number of right NOs, then the number of collisions should double. Well, NO is NO, so if I double the left NO, the right NO's got to double, right? And so when I double the concentration of the left and the right NO, the number of collisions quadruples. And so this turns out to be second order in NO, and that's just its coefficient. And then C, if I double the O2, then that should double. And so when we see this, then we see a direct connection to this. The reason we didn't see a direct connection before is because there are hidden steps. Like, for example, in the combustion of methane, you know, there are potentially thousands of different paths that can go. And so we don't know, but in this case, it's just a simple collision. And so here, what I have is I have two NOs colliding with an O2. This gives me two NO2s. And so if this were a fundamental, that is, if this were a single step, then the rate is just equal to K NO squared times the O2 to the first. So it's first order in O2, second order in NO2, third order overall. So for this to happen in a single step, what do we have to have? We have to have enough energy, and so we want to have to crank up the temperature, and we have to have the correct orientation. And so how are these molecules going to be oriented? Because I'm going to form NO2. And so if I have an NO, see, I'm not going to draw the full Lewis structure. Let's say here's one NO. Here. And say here's another NO. How do I have to have these collide? Let's start with this. Well, then I have to have it like this, right? I have to make sure that this NO is going this way, this NO is going this way, and this O2 is going this way, so that, you know, they collide. So when I have a collision like this, I can figure out what bonds are breaking, what bonds are forming. when I try to figure out what bonds are breaking, what bonds are forming, that's what we call a transition state. And so here we want to see what's happening between, this is the reactant, this is the product. We want to see what happens in going from the reactants to the products. The products are just two NO2s here. And so what's going between the reactants and the products is, boom, I have to have enough energy, right, so that I break bonds. And in this case, I need to break the OO bond. And as I break the OO bond, I need to form the ON bond, something like this. This is what we call the transition state. The transition state shows, how the bonds are breaking and the bonds are forming. And let's say overall this reaction is exothermic, right? And so the reactants are higher in energy than the products, but because of this hump here, it's initially endothermic. I have to overcome this barrier, which is the activation energy. And then it falls to the product here. And so normally when we draw an energy level diagram, our energy level diagram looks like this. We have our reactant here and our product down here, and we draw it in line. And so this is a typical energy level diagram, and we either use enthalpy or internal energy. Do you recall the difference between internal energy and enthalpy? Which one would be more useful for us? To have an enthalpy diagram or an internal energy diagram? Yeah, for us, an enthalpy diagram would be more useful, so we can see enthalpy here. Well, this is the same thing, enthalpy here, except we spread it out so that we can see what happens in going from reactant to product.
Why is enthalpy used for
Yeah, actually, why is enthalpy more useful than internal energy? Does somebody know? Did somebody tell you? You can measure internal energy also. No, this is both are given off or consumed. Internal energy what? Well, both are going to change here. Internal energy, you could have delta H or delta U, it doesn't matter. It would be delta H. We could also have delta U. It has to do with the definition. What's the definition of internal energy and what's the definition of enthalpy? Internal energy is heat plus work. That's one of the definitions. That's a change in internal energy. The change in internal energy can either be energy, because energy is conserved, right? And so it could either be energy gained or lost as heat and or work with the surroundings. First law of thermodynamics. But that's not really the definition of internal energy.
Internal energy is the total energy contained in a thermodynamic system, and then enthalpy is
Okay, internal energy is the total energy, right? The total energy. So, aren't we interested in the total energy? Are we only interested in part of the energy and not the total energy? Like we want to ignore part of the energy? Is that why we're using enthalpy? Because if the internal energy is the total energy, shouldn't we be concerned with the total energy and not just the partial energy, if there's such a thing as partial energy? Is that what enthalpy is? Is enthalpy partial energy and internal energy total energy? Okay, the reason I'm asking you this is because the next chapter after 14 is chapter 19, thermodynamics. And so you have to have these definitions down. And a lot of people either never learned the definitions or forgot them. You're right, enthalpy is going to be better for us. Why? Because we can ignore some energy. Different parts of the energy. So what part of the energy would be enthalpy? Different parts of the reaction? Well, I like someone this morning said this. Enthalpy is going to be more useful for us because they saw lots of H's and delta H's in the book. And therefore, we have a lot more numbers with delta H's than we have with U's, you know? And so it's going to be a lot easier, right? Oh, well, that's true, too. But why isn't our book filled with delta U's rather than delta H's? Well, this is stuff you want to review. This is, you know, if chapter 7 is shaky, you don't remember much of it, go back and refresh your memory on chapter 7. You'll need it for this chapter and chapter 19. But let me tell you, enthalpy is a lot easier for us because enthalpy is for constant pressure conditions. And internal energy is for constant volume. And most of the reactions that we do are constant volume or constant pressure? Constant pressure. When we're dealing with constant pressure, do we use Avogadro's law or Dalton's law with gases? If we're dealing with constant pressure, we use Avogadro's law. We don't want to use Dalton's law. Is not valid under constant pressure conditions. And so when we have a gas mixture like this, you know, I wouldn't say I'll take 2 atmospheres of NO and 1 atmosphere of O2. That would be Dalton's type mixture. I would say I'm going to take 2 liters of NO and 1 liter of O2. That would be an Avogadro's type mixture. And so in the next chapter, we deal with constant pressure typically. And so this is going to be much more useful. And so anyway, what we do is we just spread out the enthalpy diagram and then kind of see what happens in between going from reactant to product. And what we call this is, we call it a reaction coordinate diagram. And so a reaction coordinate diagram is just this enthalpy diagram that's been spread out so that we can see what happens in between. And it might be a simple step, a simple single step like this, right? But if we were to spread it out for combustion of methane, we're going to see a whole bunch of steps in between, like a multi-step. And so when we have a simple process like this versus something like this, you know, if we're just given a generic reaction like AA plus BB plus CC, and it's not specified. You know, for example, we don't know, is that a single step or is it multiple steps? Single or multiple? If it's a single, then we call it a fundamental process. If it's multiple, then it's just what we call a net reaction. And so single means fundamental, nothing hidden. Multiple means net reaction, you know, is what we're seeing here. And so if there's multiple steps, then we don't know, you know, which of those steps is the slowest. And so what we have to do is we have to use M, N, etc. As the molecularity or the order with respect to each of those. Whereas if it's fundamental, then it's very easy. If it's fundamental, then the rate is just equal to Ka to the little a, B to the little b, etc. Because we know the molecularity because we could see it based on the collision. I mean, I got 3 molecules colliding here, so if I double, if I double the NO, the rate should quadruple because I'm going to have twice as many collisions here, twice as many collisions here. If I double the O2, then I'm going to have twice as many collisions. So molecularity is easy. Here, that is the order. But when we have multiple steps, who knows which one it is. So initially, it could start off with a step like this. It doesn't even have to be 3. It could just be 2 colliding, like an A and B. An A and B collide, and they make some kind of transition state here, for example. And then we might end up with an A and a B. So we're kind of breaking the bond here, and then we've broken the bond, and we're here now. But then there could be another step where C comes in here. And the B and C might react. And so we end up with an A plus BC, and as the BC reacts, it forms some kind of transition state, which bonds are broken, bonds are formed. And then we might have another reaction in which the A, B, C react. Something like this, so we end up with ABC. And so we don't know what's hidden here and which of these steps is the slowest. The slowest step is going to have the highest energy barrier. And so the highest energy barrier we look at, for example here, this is the activation energy that we have to overcome. In this case, here's where we're breaking the bonds and forming the bonds here. And then if we look at the second step here, the activation energy is a lot smaller. So this step is going to be a lot slower because the population is going to be a lot fewer that's required. But when we go to this last step, take a look at the last step. The last step is going to have the largest activation energy in this particular example. And so that means that this is going to be the slowest step. And so it doesn't matter how fast step 1 and step 2 are. What matters is how fast step 3 is, because everybody has to go through these 3 steps to get the product. And so step 3 is going to dictate the speed of the reaction. And so this is where M and N originate from. M and N originate from the collision that's happening in step 3. Whereas if it's a simple single step, then A and B just originate from what's happening here in that simple step. And so what we don't see is if it's multiple, let's say it's a 3-step mechanism, we don't see the individual steps here. We just see the reactants going to product, and we don't see what's happening in between. Well, with the mechanism, we want to see what's happening in between. And so it could be that the 3rd step here is RDS. All right, this turned out to not be, we'll come back to this one, but this is a possibility here. So I'm going to come back to this particular problem. Let's look at another example problem here, and that is the H2 plus 2ICl. H2 plus 2 ICLs yields I2 plus 2 HCl's. And so what I see here is the net reaction. If I see here the net reaction, then I don't know, what the slowest step of the mechanism is and what it involves. And so all I can say about this particular reaction is that the rate law should look like this. It should be KH2 to the M ICl to the N. All right, then what we're going to do is we're going to measure the rate law. using whatever, method of initial rate, pseudo M, whatever we do. And when we measure the rate law, the rate comes out to K H2 to the first ICL to the first. And so this tells me that, in this particular reaction, if I double the H2, the rate doubles. If I double the ICL, the rate doubles. And then I try to figure out the mechanism based on this. And the mechanism is just going to be collisions. And so let's try to guess the mechanism for this. All right, my first guess is going to be this. I'm going to guess that there is a single step, and it's going to be a termolecular step. Single termolecular step. Okay, a single termolecular step is going to look like this. So I'm going to have my H2 and ICLs. So I have an H, and ICLs, two of those. And I want these three molecules to collide. And so how should I get these to collide to generate the product that I want? Well, when I look at it, it looks like I need to form HCl. So I want the H2 to come from below here and do something like this. And so I need the ICLs to do this, because I got to form I2. So the ICLs should collide so that the I's start to bond form here, and the ICLs start to break bonds. At the very same instant of time, I need an H2 to come in here so it can form a bond with the two Cl's, and the H bond can break. And so the transition state would look something like this. And so what I need is I need enough energy. That is, these have to have enough energy to break the bonds, and I have to have the correct orientation. Okay, and then this is going to fall apart. This is called the transition state. The transition state is just a fleeting snapshot of the reaction. I mean, it doesn't last. And then we go down to products, and the products are going to be I2 and 2 HCl's. There we have. And so we could just do this in one simple step with one collision. Okay, if we have something like this, then the rate's going to be simple, because if I double the hydrogen, I'm going to double the collisions. If I double the ICl, I'm actually going to quadruple, because if I double the ICLs, I'm going to double the left ICL and the right ICL. And so that's going to require, result in double these collisions and double those collisions. And so the rate for this is going to equal K, H2 to the first, ICL, the left ICL first, and the right ICL the first. So in other words, it's just going to equal K H2 first order, ICL second order. Do you see that? But when we look at this, this is the observed rate law. And so what's more valid? My theoretical interpretation of the collision that might happen, or the observed experimental rate law? The observed, I mean, this is experimental fact, and I see that my rate does not match this. And so they're inconsistent. This mechanism is not consistent with the observed rate law. Typically, termolecular steps are low probability. Do you know why termolecular steps are low probability? Because the frequency of this collision occurring is exceedingly small. I mean, everything has to be lined up perfectly with three molecules, and they have to be in sync. i.e. that collision has to be perfectly timed. And so, I didn't have much hope for this mechanism working, to be honest, because I already knew termomolecular steps are low probability. I mean, it could happen, depends on, how constrained that orientation has to be. And so maybe it's not a termomolecular collision. What's much more probable than a termomolecular collision is a bimolecular collision. Okay, so the termomolecular was a failure. It's a failure because it didn't agree with the experiment. But a bimolecular collision just seems a lot easier to do. Bimolecular is just take two molecules and collide them. We only have two choices of bimolecular collisions here. The two choices are this. An H2 can collide with a ICl, or two ICLs can collide with each other. Those are the only two choices because I only have three molecules to work with in this collision. So which of these do you want to do first? Or do you know which one occurs? Actually, we don't, so we just guess one of them. You want to do the ICL plus ICL? Okay. And so let's try ICL plus ICL. When ICL reacts with ICL and collide, what can form? Yeah, we can form iodine and chlorine. That's pretty good, iodine and chlorine. And the orientation's not so bad. I mean, I just have to have the two lined up like this, right? Boom. Make a transition state like this. What would the transition state look like? The II bonds would be forming, the ICL bonds would be breaking. So it'd look something like this, here, with some kind of activation energy. And so that looks reasonable. But are there other possibilities? What else could form from this? I2Cl, like this, plus atomic chlorine, chloride. Or, how about this? I could form two iodides and two chlorides. Aren't iodides and chlorides more stable? Hmm? Yeah. But there's a problem with these two. Do you know what the problem is? The problem is with the charge balance. Where did the extra electron comes from? The net charge on the left has to equal the net charge on the right. The extra electron came in here. Where did it come from? I don't know. And so these two are not possible. What might be possible is I form two I pluses and two Cl minuses. How does that look? Here the charges are balanced. But does that look good? It doesn't look so good. If I had a choice between two I pluses and two Cl minuses, I'd probably pick I2 and Cl2, right? Maybe it's two iodides and two Cl pluses. Does that look good? That looks even worse. I'd probably discount that. So far this looks to be the best here. But is that my product and have I used up all my, no. And so there must be more steps. So this is just the first step in a multi-step mechanism. So it's not going to be a single step. And then the next thing we'll look at is the other potential bimolecular collisions. So we'll take a break and then we'll look at all the potential bimolecular collisions and then see which one we like the best.